day, we have basically done everything that I wanted to do about uh, the basics of Maxwell's equation, and also the Lagrangian, the action principles in ED, okay, and associated conservation laws and stuff like that. And from today, I would basically start with relativity, so special theory and ED, and how they come together. Now, just for the sake of completeness, so last day we sort of showed in a very simple way, I think very beautiful way, that the energy or the momentum that travels with a speed, and that speed is basically the speed of light. So although in the beginning we had assumed that the electromagnetic waves travel with the speed of light, over there that was assumption. Over here we showed, and it's a very simple way of showing, but it's very nice, I think. Showed how, if you think of a wave packet, and if you think of how the energy is traveling the wave packet and how the momentum is traveling the wave packet, then both of them are traveling with some velocity, and that velocity is basically the velocity of the speed of light, which is c. Okay, and that gives you basically a physical basis of the speed of light and connects it to the velocity. Now, the other thing we wanted to do is that this conservation laws, from which we basically got this speed of light and the velocity, the electric field and the magnetic field, they have to have a certain dependence. Okay, and we know what it is, that they are perpendicular to each other, but that also comes from the conservation law. So let me just quickly do that. Okay, and then I will go into the special theory. So if you look at the equations that we had last time, let me see over here. So this equation, from this equation, and then the momentum equation, and the fact that we have this Vp times P is E, these equations. From these equations, we see that, one can hold. So basically, from these equations, we have the relations that we already know between the energy and the momentum and the speed of light. So you have your energy, okay, which was times the momentum that you can see, and your momentum was mass into velocity, but mass we saw that it was E by c squared, okay, times the velocity. So you got your E equal to Pc, okay, and your B is equal to basically C, but it is basically, sorry, so these two relations we know. Now we will go back and rewrite these relations a bit, and we'll rewrite these relations and try to see, for the sake of consistency, what we get. So if you write the equal to PC relation, this relation, okay, if you write it in terms of the fields, okay, over here, of course, is the energy, not the electric field. I can write this in terms of fields. You write it in terms of fields. Then you'll see over here, we have the volume integral of energy, which is E squared plus B squared by 2, okay, 8 by 7. And this is basically equal to, if I cancel the C, then this momentum is written in terms of E cross B. So d cube R, okay, so E cross B by 4 pi. So C was here, so you can cancel the C. Okay. Now, if I look at this equation, then we know that if you have multiple vectors, then the sum of the multiple vector, of course, will give you a vector, and that will be maximum only when all the vectors are in the same direction. So obviously the A plus B, if there are two vectors, they will be maximum if both the vectors are in the same direction. If they're in the opposite direction, they will cancel. If any other direction, they will be components, it will never be the maximum. So maximum happens for multiple vectors from this addition if all the vectors in the same direction. So if you can write it like this, okay. So basically, if you write it like this, sum of vectors are maximum if they all point in the same direction. Okay. So it basically tells me that I can write an inequality over here, which is d cubed r, okay, b squared plus b squared by 2. And this is basically equals to. And this equality will happen when they are all in the same direction. So this is one thing. Okay. So equality of this happens when E cross B, only when this E cross B everywhere points in the same direction. So equality happens when E cross B same direction. Okay. That's one thing we can write down. Now we can also try to do a little bit of juggling with the E cross B. So now what I'm going to do is I'm also going to do a little bit of juggling with the E cross B. So I can write it E cross B like this also. Okay, I can write down my E cross B whole squared. And this is basically E squared B squared minus E dot B whole squared. And this, so this, you see, this is nothing but E squared plus B squared by 2 whole squared minus E squared minus B squared squared E dot B squared. Okay. So I can rewrite it like this. And so you see this E cross B is basically less than or equal to this first term. So this is basically so if I make this thing take R equals B, this So over here, so okay, I'm jumping steps. Let me put it over here. Let me write it like this. So what do I mean? Over here, as you can see, the equality will hold if e squared minus b squared by 2 is 0, that is e squared is equal to b squared, plus e dot b is equal to 0. If these two things are equal to 0, then this equality will hold. Otherwise, I'm always subtracting out something, so it will always be less than e squared plus b squared by 2 whole squared, right? So for the equality to hold, both e squared minus b squared by 2 has to be equal to 0, and e dot b has to be equal to 0, or e squared equal to b. Therefore, dqr e plus b, this thing is equal to dqr Now, if I want to compare both of this equation, and this equation, okay, these two equations will only hold, these two things will only simultaneously hold if the two green equations will only simultaneously hold if first, of course, we know that e squared has to be equal to b squared. So if e squared is equal to b squared, number one, and e dot b is equal to 0, which basically means e and b are perpendicular to each other, plus e cross b is unidirectional, okay, along direction of propagation. So the arguments that we had that connected the conservation laws locally within the pulse with the speed of light, and that gave us a equation between the energy and the momentum, also leads us to this kind of argument that locally within the pulse, your E and B has to be perpendicular to each other. The E and B has to be same, and everywhere as the pulse moves, the E and B has to be perpendicular, where the direction of the propagation is also perpendicular to this. It has to be unidirectional, this E cross B. The direction of E cross B has to be along the direction of the pulse, of the movement of the pulse. These three things comes from over here. And so,
Sir?
yes.
Sir, can you say once again that why it's necessary to have the maximization of the sum of the vectors that results into the unidirectionality of the E cross B?
No, why is it? Because, what do you mean? Why is it necessary? Ah, no, no. The second one you are talking, E cross B, this whole square, right? Hello?
No, sir. You have written a statement.
Because
One second.
because
Some of the vectors are max.
E is equal to PC, right? So this has to be equal to. So maximization has
Okay.
to be there.
Yeah, yeah. Yes.
So the
Sorry.
whole point, the whole thing came because we could get equal to PC, and that came
Yes.
because we had the velocity and the C. So this is how all this thing is tied up together.
Yes. Yes.
Okay, so I think with this we will really come to an end of the initial lectures on Maxwell's equation and its and invariance laws and conservations and stuff like that. Next, we will start with relativity. So I want to start with relativity today. But what I'm going to do is I'm going to be a little casual in the sense like for the first class of relativity, you guys have already done relativity before, but I still have to do certain things before I can connect ED with the special theory of relativity. So there has to be the basics that have to go through. So I don't want to, spend time writing those basics. So today, in the first part, where I talked about, where I basically do a recap of things that you already know, I'm going to show you, I've already written it down, so I'm going to show you this so that we can move fast. Okay. And the next day, we'll start, do the Blackboard stuff again, because we're going to connect EM theory with relativity. Okay. So that's my plan. So with that, let me try to get rid of my iPad and share something from my laptop. Okay. So stop share over here. Then I need to share here. But where is the good share? Share screen. Just a minute. Let me try to. Okay, now I need to share. Where is the share in my laptop? Start share. Right. So you can see this, of course, hopefully. So my job is quite easy over here. I'm going to very quickly go through the basics of special theory. Okay. And then with this basics, the next day we are going to define how ED meshes up with special theory. Okay. So this is basically a notes that I wrote for last year. So I'm basically just showing you the notes for last year, from the last year. So I shared the same notes last year. This is basically ditto what I shared last year. Okay. So start with, we should basically understand that the special theory stands on two postulates. So there are basically two postulates of special theory. First, number one, that the laws of nature are the same in two reference frames with uniform relative velocity. So that's very important. If you have a uniform relative velocity, then the laws of nature, the laws basically the equations which connects two variables, they are basically the same. They should come in the same form. And when I talk about uniform relative nature, I mean with no rotation. Okay. That's first. And the second is the postulate that the speed of light c is the same in all such frames. So in all these frames, everything which has a Galilean invariance previously, which moves separately from each other with some constant velocity, the speed of light measured in any one of them is always c. So there is no plus minus v with the speed of light. The speed of light is always, so this is the basic two postulates. And with this postulate, we can build up all the different transformation laws that we know in special theory. So to do that, of course, we start with these two reference frames. Okay, one I call K and another I call K prime. And these are basically orthogonal reference frames, X, Y, Z, very simple. Origins are O and O prime. And the K prime frame moves in the X direction, the positive X direction with the velocity v. So this is our definition. We could have, depending on the books you follow, some books will have it as the primes will be different. So you have to be careful. Okay. So what will happen is in the relation, sometimes the plus v will become minus v. In fact, if I remember, the first day I gave this in the class quiz, there was someone who actually asked me whether about this plus and minus velocities and stuff like that. So you have to be careful about that. Okay, so v is this uniform reference, uniform velocity, and the idea is that the origins coincided at t equal to 0. That's for our choice. So our choice is that we'll start when the two frames were on top of each other at t equal to 0, and then it starts moving. Okay. Now, if a pulse of light is emitted at t equal to 0, so I will go slowly through the arguments over here. It's very simple. If a pulse of light is emitted at t equal to 0, each observer in each of this reference frame will see an expanding sphere centered at its own origin. Okay, this is due to the postulate number 2. So you move, the speed of light of course does not change, it moves at the same velocity. So each of them will see that a sphere is increasing out of their origin with the same velocity. So they all expand with the velocity c and measured from their origin. So first of all, this is inconsistent with Newtonian because center always at t equal to 0 is at rest. In the second case, it is not at rest, but you still see that the sphere is moving out at speed c. That is a postulate. So the reconciliation over here is that the connection of the space and time particular to each observer, and it is not universal. So the reconciliation over here, again I am saying, is that at each place, the connection between space and time, it is basically defined for that observer. It is not an universal connection to space and time. To see that, what we do is that we expand, write down the equation for the expanding sphere for both this x and x prime coordinates. Okay. So for x coordinate, because it's expands the speed of light, it is x squared plus y squared plus z squared minus c squared t squared equal to 0. And similarly, for the other one, it is x prime squared plus y prime squared plus z prime squared minus c squared t prime squared equal to 0. So here in writing this itself, we have used the postulate that the c is the same. If it was a Newtonian, then we would not have written c over here. We would have added the velocity or subtracted the velocity of the frames. Now, t prime is not equal to t as in Newtonian. Okay. With the postulate of homogeneity and isotropy of space, saying that each directions is basically the same, and in other than having the two reference frames perpendicular to each other, I could have rotated each of them and then looked at it. So that is the isotropy and homogeneity of space. This equation, both these equations can be satisfied if there is a transformation between x and t. So I have to think of some transformation that will satisfy these two equations. It's as simple as that. Okay. And it turns out these transformations are the Lorentz transformations, so that for each frame, your sphere, the light sphere, expands at the same speed. To do that, I need to have this, because I need to simultaneously satisfy these two equations. And this can be satisfied if there is transformation between x and t, and the transformations are what you know as the Lorentz transformations. Okay. So x prime is gamma x minus vt, y prime is y, z prime is z, and then t prime is gamma t minus v by c squared x. These things you know very well. Of course, you can immediately write down the inverse transform. The inverse transform is just changing the v to minus v. And so the inverse transforms are like this. So just from the two postulates, very simply, just from these two postulates, that the speed of light has to be the same in each of this coordinate system, and the fact that basically means for each of these coordinate systems centered around its own origin, there's an expanding sphere. Write down the equation of the sphere, and the only way these two things can simultaneously over here in terms of language, not in terms of science, can be satisfied is if we have this kind of connections between x prime and x, y prime and y, z prime and z, and t prime and t. And these are the Lorentz transformations. So that's as simple as this. So since space and time both transforms, the basic unit, of course, is event. So Lorentz transformation always applies to event. So you cannot have one changing and other not changing. You have to change both. So as soon as you write these transforms, you can immediately go and write down all the other things that are basically byproducts of this Lorentz transformation. Okay. So even if you know these things, it will be good that you just listen to this, what I'm saying, and basically look up this thing, although I put it up, because it's a good revision of all the very basic things that I want you to know, and you will be doing problems from this. So it's good to, I mean, even if you think, oh, I know all these things, don't just go away, keep staring at the screen, listen to what I'm saying. So next we do length contraction. Okay, so this is the first byproduct of Lorentz transformation. Okay. So in K prime, we define a length L0, and L0 is defined by having the two ends of a rod, the length having x2 prime and x1 prime. So two values for the ends of the rod, x2 and x1, because in a prime, there is x2 prime and x1 prime. So x2 prime minus x1 prime is your L0. In K frame, it will be x2 minus x1. Okay. Now, the important thing to understand, and this is something that is used in many places. For example, if you do cosmology, some of you, to measure a length, you need to measure the two ends at the same time. Okay. That's very important. I cannot say that I'm measuring the x1 this side of the rod at some time, and then I'm measuring the other side at some other time. If I want to know the length, I need to measure it at the same time. So at the same time, your L0 is x2 prime minus x1 prime, and that is basically gamma, because x2 prime is gamma x2 and x1 prime is gamma x1. So this is gamma times x2 minus x1. And x2 minus x1 is basically the length in the unprimed coordinates, so gamma L. So it basically tells you that the length in the unprimed coordinate, the one in which nothing is moving, so the stationary frame, that one is basically the length which is in the moving frame divided by gamma. So this is why it is a length contraction, because your gamma over here, so V is always less than C, so the denominator is always less than 1. So gamma is always more than 1. So over here, whatever is the length in the reference frame in which it is moving, the one in which is not moving, it is always small. So typically this basically means that if I am looking at something which is moving away, I will measure a length which is smaller than what is the actual length of that object. So there's something in the sky which is very fast. I will measure it, the length of that object, cosmological object, I will measure it to be smaller than what it is. So this is the length contraction because the rod, the length appears shortened by 1 by gamma.
Sir, the measurement has to be at same time t prime, right? Rather than
Measurement has to be at the same time. You are measuring over here at the unprimed coordinates. That's where you're measuring, right? I'm measuring over here. So I am at the laboratory and I'm measuring. If I'm going to go to the t prime, then I'll measure at t prime, but then the coordinate transformation will be exactly the opposite.
No, I mean, when we are saying L0 is x2 prime minus x1 prime, then x2 prime and x1 prime are defined at t2 prime and t1 prime, and t2 prime is not equal to t1 prime here. Is that so?
No, don't think of it. Okay, think of it like, I don't know how to think of it as that I am sitting over here and there is some object which is in a reference frame which is moving fast. If I want to measure the length of that object, then I want, so if I want to, so we look at the coordinate transformations over here. The coordinate transformations over here also, I'm changing my time t, right? In this coordinate transformations, because it's moving away. At any point of time, I'm changing, but at any time, my x prime and the x needs to have a simultaneous measurement. So over here also, that's the same thing. So if I want to measure if I want to look at the size of the two objects, the two photons must come to me at the same time. I want to see it at the same time.
I get it, sir.
T prime, see the T, see, okay, I understand what you're saying. See that the important stuff is that the two photons must come at the same time. So at the same time, irrespective whether you want to think of it as T or T prime. So think of it like this. If I want to measure the two photons that is coming from the two ends of the rod, and they, in their coordinate system, they have a T prime, because they are emitted at the same time, I also get it over here the same, another time t, which is exactly also the same t. It's not a difference. So the whole point is that the two photons from the two sides must come at the same t. It is not, okay, so it is not t in the sense of, it has to, so let me not write this. If I cannot rub it over here. Measurement has to be at the same time. That's the important point. Okay.
No, sir. What I'm saying is that measurement if we measure two events at the same time in one frame, it won't be simultaneous in the another frame, right? So you can only measure simultaneously in one frame. So basically, the way you are defined is L0 won't be the proper length of the rod.
Why not? It's the same event. It will be exactly the same. So time T1 related to, so think, I don't know how to say that. These are the same. T1, T and T prime has the same relation. So if both photons are released at the same time from there, if my stamp is T prime for both of them at the two ends of the rod, the stamp is T for both of them over here. It is not different. So do not bring that simultaneity over here.
So T2 prime minus T1 prime is non-zero.
Huh?
T2 prime minus T1 prime.
That's what I'm saying.
Minus gamma.
No, but you don't say T2 prime. That's the whole point. If you want to measure it, both the photons has to be such that it should, that difference has to be such that they should come at the same time to you.
Exact.
Otherwise, you do not measure it.
So we are measuring it in one frame with the unprimed frame, right? At the same time, we are not measuring in the same time in the prime frame.
What I'm saying is, both the photons from these two sides should come to you at the same time for a measurement of length. It should not come at two different times for the measurement of length. The measurement has to be at the same time. Otherwise, how are you going to measure it? And the length definition itself, think of, I don't know, think of a, let's say, these things become even more complicated when you, let's say, you want to do some kind of distance measures in the real universe. All things are happening. Things are expanding. Light is also having some speed. The expansion is also having some speed. So it's traversing a different length scale than a straight path. Straight path means depending on the expansion. But if I want to measure some rod somewhere, some size of a galaxy, the photons from the two sides of the galaxy must come to you at the same time. If they don't come to me at the same time, then I cannot measure it. Now, we can say it is continuously emitting. That is different. But suppose it's not continuously emitting. Suppose there is just one bip over there. Unless they come to us at the same time, I do not measure it. I cannot measure the size of the rod. That's the basic assumption of measuring a size of the rod. I want to see the rod totally in some sense. So in one photograph, so measuring the rod means I'm taking a photograph, right? For the photograph, for the rod to appear in that photograph over here, both the photons from this and this should come over here at the same time. Otherwise, how will you get a photograph? So your arrival should be at the same time. That's the whole point. Both them should arrive at the same time. So it's measured at the same time over us. Is it still confusing or like?
So, but whether that same time is unique in two frames.
No, don't think of it. Forget about. Don't think of it in complicated, unique, non-unique thing. I have.
No, I mean that. Say in unprimed frame, the two photons are coming at my detector at some time t, and in the prime frame it is coming at some time t
I
prime.
don't care about prime frame. I only care about unprimed frame. Suppose I have a very fast camera, infinitely fast camera at an unprimed frame. Okay, I'm taking pictures. Click, 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 click. I will only click the picture of a rod if all the photons from that rod come exactly at the same time at my camera, because that's the clicks. That's infinite resolutions, right? If it happens that one end of the photons has not come to us, then I don't see the rod. I only see one end of the rod. So the length over here is defined only by the fact that it should come at the same time. That's how it is. And then when it comes at the same time, I can measure what is the X. But I know that the X primes over there, just because I know inherently what is the size of the rod, that I know inherently. Then I will see that this X2 minus X1 will be smaller than the inherent X2 prime minus X prime 1, X1 prime. That's the whole thing. Because you cannot argue both ways. You cannot cancel one with the other. If you do that, then you will not have time dilation. Then length contraction comes exactly the same way it will go, you have a time dilation. Over there, it will not be the same time. Over there, it will be something different. Right? Then you do not talk about the same time because there is a time interval then. Over here, to take a photograph, it has to be at the same time, at the left. Think of just in terms of a camera taking photographs. That's the simplest way I can think of. In fact, you will see that to have this effect to be symmetric, again, it will make sense if then it has to be over there at the same time t prime. Only then you will see that this effect will become symmetric, because then it will be multiplied. Not multiplied, it will be divided. Otherwise, it will be multiplied. So depending whether you are in this frame or whether you're in that frame, you will always get your sizes which will be smaller. Otherwise, it does not happen. If you think of it if you don't think of the two photons coming to you at the same time. See what I've written over here also. So effect is symmetric. If the rod was in the reference frame K, then K prime would again measure it 1 by gamma. However, to make things a little more complicated to understand, however, each observer would see two ends of the stick not marked at the same time. Okay. So now if there was some universal clock with which I was mapping these things, the observers will not see these two ends of the sticks marked at the same time, which by the other observer. So other observer will be marked at some different time. So the whole point is that in this thing, the Lorentz transform of time depends on position. Temporal simultaneity is not a Lorentz invariant quantity. So there is nothing called temporal simultaneity over here, because it's not Lorentz invariant. It is not always so easy to understand, to be honest. But I would basically suggest the best way to understand is to think of in terms of camera taking pictures in this frame, or if you want to go over there, camera taking pictures in the other frame. So whichever way you will go, you will see that if I want to take pictures over there, then my size, once the picture is taken, the size will come out to be smaller. So the same way we basically do time dilation, just like in length contraction. So time interval T2 and T1. So the clock over here, so this is a slightly more tricky. So the clock is at rest at the origin of K prime. So the K prime, the clock is at rest at the origin, but K prime moves with respect to K with velocity. So the clock is at rest at the origin of K prime, and X prime is 0. Because the clock is at rest. So the X prime is always 0 because the clock is at rest. But K prime moves with K with respect to velocity v. Then you will see that this in the K prime, in the K frame, the T which is T2 and ST1 will be this. Because this is how simple this is. Over here, the rest of the things, X prime is 0, so all this things becomes 0, this part becomes 0, so only this thing remains. So again, it is symmetry between K prime and K, and this is the time dilation because the length of the time period increases. Velocity transformation comes very simply. If I know how the time changes and how the position changes, I take the ratio of this and I'll get velocity. That's how velocity transformation comes. As simple as that. So if you think of again the two seeing? So you have some velocity in the K prime frame, which is actually, hold on. You cannot see my pointer over here, right? When I put it on the board, does it come?
Yes, sir.
You can see the pointer. It shows in the thing. Okay.
Yeah, I can see.
Okay, good. So for example, now I am pointing at this velocity. I'm hovering my thing over on the velocity, or you can see it on top of the velocity. You can see or what? I don't know. I can't see.
Yes, sir. Yes, sir.
You can see your cursor.
I can see. Good, very good. Yeah. So in the K prime, you have some arbitrary direction in which the velocity is there, and we call it U prime. This is the velocity of some object, which is not the velocity at which the frame is moving. So you differentiate between this V and the U prime. And it is in some direction. So I have an angle, theta prime. So what is the velocity? So basically over here again, x2 minus x1 was dx. So I can write down my dx, dy, and dz and dt in terms of the gammas. Okay. So this is exactly the Lorentz transformation, just x becomes replaced by dx and dt becomes replaced by dt. Okay. This thing happens. And so your ux is dx by dt. That's your velocity. So if you have ux by dt, then I can write it down in terms of x prime. So basically now what you're seeing is that over here, you have all the components of the velocities which is changing. So your ux is changing, your uy is changing, and uz is changing. Although the velocity of the two frames is only in x direction. So that's important. Although the velocity of the two frames, they are moving only in changing in x direction, a velocity of some particle in one frame has all the components changed in the other frame. This is simply because of this thing. So it's not very difficult, it's quite trivial to do. Now we can always write it in terms of, so I gave you a problem in which I've asked you to do it in terms of vectors. But one very important thing to do over here is to, instead of doing it Vx, Vy, Vz, instead of doing of Ux, Uy, Uz, if you just take the perpendicular and the parallel components. So one component along the motion of the frame and another component which is perpendicular to the motion of the frame. So basically you have a velocity u, you decompose into u perpendicular, u parallel. So u parallel is along the motion of the frame and u perpendicular is along the perpendicular to the motion of the frame. So over there, you will find this will be the relations between the parallel and the perpendicular components. Now the reason we do it like this, because from here we can come to many conclusions. Okay. First of this is this aberration formula. Okay. The aberration formula is basically the ratio of the perpendicular to the parallel component. So if you write down the aberration formula, ratio of the perpendicular to the parallel component, okay, given by some theta. So theta, I remember, this was theta prime. So equivalent angle between y and x and the u will be theta. So in the k prime, theta will be the angle over here. Okay. So in the aberration formula, you will find that this tan theta, which is u perpendicular or u parallel, is written in terms of the components in the thetas and the component in the prime frame. This is simple to do. But the next step is interesting when we get is that azimuthal angle phi is of course not changed. So because perpendicular x, y direction, z direction does not behave differently. So what happens when u prime is c? So this is an interesting question. So if you are traveling, if you have a light, if you have a photon in this other frame, what happens when u prime is c? So in that case, you will see that you can write down this tan theta and cos theta over here. And these are the equations for aberration of light. So this is something that we are going to use many, many times. So every time we talk about radiation emitted from a charged particle things like that. Over there, the photon emitted is basically traveling at the c, and then you may have frames that are rotating and stuff like that. So this aberration of light formula will be used many times. Okay. So over there, if the velocity of the particle itself is the velocity of light, then you can write down these two formulas for the aberration of light. And then this gives us some very important corollary to it. First of all, this thing, what happens if the photon is emitted at right angles to phi? So remember, the k prime is moving along x direction. Okay, so this is how the two frames are moving. The velocities are changing in the x direction. A photon is emitted perpendicular to x direction, right angles to phi. Okay, so it's emitted in the yz plane. Okay. So in that case, your theta prime is 90 degrees because theta prime was the angle from x to the velocity. So theta prime is pi by 2. And then your tan theta becomes c by v gamma, and your sine theta is 1 by gamma. So now it tells you that if it's highly relativistic, so something which is very, very highly relativistic, so it's large gamma, then this theta is 1 by gamma. This is a very, very important relation, that if I have emission which is highly relativistic, or if it's a photon, then the angle, so if it was this angle that was theta prime was pi by 2, theta, remember, is the angle that you see in the unprimed film, so what I'm seeing. Okay, that angle is very, very small. So all your photons comes at an angle which is very small, because gamma is very large, so 1 by gamma is very small. So this is what is known as beaming. So something, let's say you have some motion going round and round, particle going round and round, it will give you emission. But what will happen is that this emission will always be at an angle which will be beamed generally along the direction of the motion. So at any point of time, if the direction is like this, the angle will be a small angle along the direction, then a small angle. So if you are there with the camera, you will only get it when that angle is along the direction of the camera. So we'll only get certain peaks because of this fact, because of this beaming. That will not happen if your velocities were less. If your velocities were very high, then this is how this beaming happens. Okay, so this is very important. So we'll come back to this again and again. This relativistic beaming. The theta is 1 by gamma. Now, because of this, you see something very interesting happens. The next thing is that suppose all the photons were emitted isotropically. So this is c, velocities are c, but all the photons are emitted isotropically. The emission is isotropic, but because of this beaming, what we see is not isotropic anymore, right? So even if this photons are emitted isotropic, remember half has theta prime which is greater than pi by 2, this half, and the half has theta prime which is less than pi by 2. And so this is isotropic photon, k prime going with the velocity v. What will happen is that this side will be separate and this side will be separate. The pattern on the right hand side will be different from the pattern on the left hand side. So what will happen is you will get something like this. In the k prime, your pattern of the photons will be like this. So this gamma that I said over here, this beaming, that gamma will be, that theta will be this. So photons are always concentrated in the forward direction. So think of, again, as I said, think of some particle which is emitting radiation. At the point it is emitting radiation, of course, it is isotropic. There is no preferential direction. So there is a bunch of photons isotropically emitting. But what you will see is always concentrated in the forward direction, inside a cone of half angle 1 by gamma. So very little photons and this region or in this region. And this is the key in understanding almost every phenomena that will come later, whether it is whether it is synchrotron radiation, whether it is Bremsstrahlung, X-ray photons, whether it is something which is known as Cherenkov radiation. All of these will basically have this beaming or this fact that photons are forward concentrated part of it. So this you need to understand. So this is called relativistic beaming, GRBs and stuff like that. In fact, for example, let me give you an example of this GRB when I said. The reason I wrote GRB is that if you do not have this beaming, then we come up with all sorts of crazy ideas. So we look at GRBs, okay, and we find that the energy of the GRB is exceptionally high. Okay. It's exceptionally high. So you think, look at the energy, calculate how much energy it can come. It comes out to be very high. And then there is a lot of question how high that energy it is. How can that energy be so high? GRB means gamma ray bursts that we must have heard. Turns out it makes things easier if you realize that again, these gamma ray bursts are highly beamed towards us. Okay. So then what we are looking at, we're thinking it high because all the energy is concentrated in a very small cone. And we thought of, calculated when we did the theory, thought of this energy, the same amount of energy over the entire volume. But that is not. It's actually concentrated in a very small cone. So actual energy is basically that solid angle of the cone by 4 pi. So then, because the cones are very, very small, okay, so the total solid angle is 4 pi, whereas the cones are very small, we have a few degrees, okay, instead of the whole sky. So then it goes down by a couple of orders of magnitude. So in real life, this is why these things are very important. And of course, when you think of in particle physics accelerator and stuff, you have to continuously look at this beaming effect to actually know what is the energetics versus the energy that we are estimating, because what you are getting is all beamed towards us. Doppler effect, we know this thing. I'm going to go very fast, you know. So Doppler effect basically, if you measure arrival times of pulses, okay, you measure the periodicity, and then you look at what happens due to how does the arrival time of pulses change compared to the original pulse timing. Okay, so you can read through this. I'm going to put it up. You will find that, you know, there is a pulse which is given by a delta t, which is gamma times 2 pi by. So observe is over here on the top. Okay, and the pulse happens. There is, remember, to have a pulse, there has to be one event and there has to be another event. That gives you a pulse. Okay. So the pulse is happening, but between these two times, these two regions which defines a pulse, this object has already moved a distance L. Okay, so one region traverse extra distance d, the previous one. So this one and this one, sorry, this position and this position, they should define the simultaneous region for given the pulse. Okay. So you calculate the L, you calculate basically L is velocity times the delta t of the pulse, calculate d, and then what you want to basically realize that the arrival time will be your delta t minus the time taken for this, okay, d by c, because only these two are coming together simultaneously. Remember, again, the same thing. This and this should come over here simultaneously in terms of language. So I'm taking pictures to know that is a pulse. So the time will be delta t minus d by c, and you can write down what is d by c, write in terms of velocities, and you get this frequency Doppler thing. So the frequency that you observe and the frequency that it was emitted, they have a relativistic Doppler effect. So there is a gamma coming over. These are straightforward applications of the initial things that we did. So all these things, you all know proper time, very easy. So this is where when you construct something out of both the length contraction and the time. So both the length and the time has the Lorentz transformation, but we construct something where a combination does not have a Lorentz transform, which is Lorentz invariant. So that is the proper time d tau, and that is defined like this. So if I have a d tau, then c squared d tau squared is defined like this. So in my definition, this is defined like this. Sometimes you can write it separately, different way, depending on whether you want to have pluses and minuses can be interchanged. But this is the metric of, I'm not able to come to metric yet, but this is how I define. The c d tau, where d tau is the proper time, is connected to the time interval dt and the spatial intervals. Okay. And over here, if you do the Lorentz transform to forget about y and z, if you do the Lorentz transform to both x and t, you will find that my d tau prime and d tau, they are the same. So d tau basically is Lorentz invariant, and that d tau basically is the time interval between events occurring in the same spatial. That's how you define. So if I think of dx, dy, dz to be 0, then d tau is equal to dt, right? So the physical definition of d tau, it is basically the time interval of the event at the same spatial location, where x, y, z are the same, x prime, y prime, z prime. So the ticks of clocks carried by the observer. So straightforward stuff. Another thing is that, d tau and dt is connected by this transformation. So if there is a proper time and if there is a actual physical time, then the proper time, which is the d tau, it is connected to the physical time by this dt by gamma. So again, these things come, people who do a cosmology course later, maybe, I don't know how many of you are interested in cosmology and stuff. You will see that we are going to use this thing very much. So next semester, probably I will do a cosmology course. So if some of you are coming to that course, then you will see that we are going to use this many, many times over there. So how all this times related lengths and things will be defined over there. Just to be curious. So okay, let's say how many students are over here right now? We have students. Can't see. Yeah, whoever, maybe there are 10, 15 of you. How many of you are interested in cosmology? Are there people over here who are interested in cosmology? Vaishak, Resident, Aranya, Resident, two people are interested in cosmology. 3, 4. Okay. That's very good. So next semester, so this semester I was supposed to do a cosmology course, but I was asked to do the ED2 again. Otherwise, I would have done a cosmology course this time. Next semester, I will do a cosmology course. So if you guys are interested, you can come. So typically every 2 years, 2.5 years, I give 2 years. Previously, I used to give it almost every year, but now there are more people in the cosmology subgroup in DTP, so we share between us. Yeah, previously I used to give it every year, maybe every 2 years. So I'll do it again. So all these things, this proper time, everything that we are doing over here will come over there, and things will become slightly more non-intuitive over there. Okay, so this is where I'm going to stop over here today. Next day, we are going to do 4 vectors, and that's when I'm going to start writing a bit, because 4 vectors we need to do a little more carefully. So we'll do 4 vectors, and then we'll try to connect our ED with the 4 vectors. Okay. Whatever I did today was very, very basic. That's why I did not want to write it. Okay. But next Wednesday, we'll do 4 vectors. And then we'll connect the ED4 vectors with whatever 4 vectors are there. And see how things go. And then go and formulate the covariant version of electrodynamics. Okay. Also, I'm not going to give you a hint. I mean, you have been doing all these Lorentz transformations the way I have did it, or typically this is the way it is done, standard way. We will, when you go to electrodynamics, we will see that due to consistencies conditions, we will derive back our Lorentz transformations from just from consistencies. So that will be interesting, and hopefully that will be new to most of you. So I think, I don't know about you, I mean, what I have done till now, most of it is not really done in ED1, although I've done Maxwell's equation, I've done conservation laws. I don't think most of these conservation laws, the way I have done it, is done in ED1. So it's slightly more technical than it is done before. So I hope that these are new to all of you, because ED is a course, ED, you have been doing ED for a long time, from class 12, first year. So it's difficult to give a course which people have already done many times. So I hope these are, at least most of you would find sufficient number of things which are done in a different way and new. Okay, so let me know. So we'll stop over here. Last day I asked you to fill in the steps of the equations. Did anyone even try? I don't think so, but still I'm asking. I mean, if you do not try it then and there, again, you will find it difficult later. Atul tried, or is it Atul? No.